In this lecture, we're going to be transitioning to a new topic of developmental psychology, but one that's related to a lot of the stuff that we've been discussing in previous lectures. In particular, I'm going to be focusing our attention in this video on motor development. Context as to where we're coming from. Obviously, in some of the previous modules, we've spent a lot of time talking about physical changes that take place in our early and latter years of life. We talked a lot about kind of the overall growth and decline of the body, and also the overall growth and decline of this general system that we called the nervous system. Now, when looking at those changes of those major structures of the body, we can either study them alone or look at how they impact one major mental aspect of our life, and that's our sensory and perceptual systems. And something very closely related to that is something that we call our motor system. We're going to be dedicating a lot of today's class on our kind of intake of touch and our motor system, and how these things actually come to be and how they ebb and flow throughout the entirety of our lives. To understand the motor system and a sensory system as well, it's probably first important to discuss why it's so unbelievably critical for us to develop this. Obviously, that one key element that allows the motor system to kind of retain its importance for all species is that it tends to allow a species to be able to detect and to avoid any dangerous situation. It can help us, say, stay out of the heat or not touch very sharp things or not use a limb that's injured. This is definitely a key element to our sensory system of touch and our motor system, but well, actually for all of our sensory systems for that matter, but it's definitely not the only thing that these systems are important for. It also gives us just general information about the world around us in a whole bunch of different mediums. It allows us to be more effective in our interactions with those things in our environment. And ultimately, it tends to help us derive some type of enjoyment, some type of pleasure with the interactions that we engage in when we're able to successfully not only understand what's going on in our environment, but engage with it in a way that we would like. And this means that even though it might really be kind of a byproduct of some of the physical changes and neurological changes that we've discussed, spending a amount of time talking about it and really focusing on how things unfold is definitely worth it in a class like this. And how these systems come about, we actually have to go back to something we discussed in our last module, in particular, the nervous system. Now, as we talked about in the previous lecture, our nervous system structurally is pretty much intact at birth. We have the two major systems that we call the central nervous system and the peripheral nervous system already up and sort of running and ready to build as well. Now, there's still some growth to go for both the central and the peripheral nervous system, but one of the things that's there and present at birth in the peripheral nervous system is this system called the autonomic nervous system, a really essential connection of nerves traveling to and from the brain that allow us to do things that are kind of done, as the name implies, automatically. It allows us to breathe, it allows us to have our heartbeat, it allows all of these different reflexory responses that we'll look at a little bit later that help allow us to kind of avoid those dangers that we were talking about previously. In addition to this autonomic nervous system, though, we also have something called the somatic nervous system, a collection of nerve fibers traveling to and from the body that allow us to really engage in a lot of the motor and sensory things that we link to the concept of touch. And understand how this somatic nervous system actually functions and what allows us to communicate with the brain, we have to understand that most of our nerves, most of our neurons that are spread throughout the body are a part of this thing that we call the peripheral nervous system and needs to form after birth. And what they come together to eventually form in these different nerves are different routes, either to the brain or from the brain for the sensory portion, which is what we often call the afferent route that's going up to the brain, or the efferent route, or the motor system that's having the brain communicate with some structure within the body, usually some muscular structure in the body, so we can move and react the way we want. That, if you're looking for kind of an interesting fact, you can see in this image on the lower left-hand corner that our afferent, or our sensory system, which is located in the spinal cord, is actually located along the back end of our spinal cord. So as you have those neuronal migration travelings of neurons throughout our entire body, coming together through the process of synaptogenesis that we talked about in the last lecture, they eventually form this afferent route that allows all the different cells that are ready to pick up on information to actually send an effective message to the brain. And once we're able to kind of figure out how to respond to those things, kind of a chicken and an egg situation there, we start to develop our efferent routes, our motor routes, where our brain can send messages, in this case, down the front of the spinal cord, what we sometimes call the caudal portion of the spinal cord. So we can get that information to the body and actually allow us to react the way that we want to react to the different stimuli that are present. And this kind of interesting notion of the spinal cord being responsible for both components of both touch and sensation, touch and movement, is kind of neat. But when you find out how it's divvied up, you really get a better understanding of how complex something like the spinal cord actually is. In addition to needing our spinal cord and the different routes to and from the brain, we also need that brain to help us with our sensory systems and our motor systems. And there's two particular areas within the brain that are really critical players in these processes. In our last class, we talked a little bit about how we had this little structure in the middle of our brains called the parietal lobe. It was located just behind the temporal lobe and just behind the frontal lobe and above the temporal lobe. Well, this parietal lobe contains a really interesting band of neuron clusters that we call the primary somatosensory cortex. It's this stretch of area that's dedicated to different parts of our body. And as our brain starts to form, as we start to develop a lot of our sensory systems with respect to touch, what we see is many neurons making connections that are in correspondence to different neurons in the body making other similar connections. So when we have this afferent route of information going from the body to the brain, it doesn't just randomly disperse once it hits the brain. It usually goes up the spinal cord through a couple paths that we're not going to talk about quite today, and eventually arrives in the first structure of our cerebral cortex or our brain, and that area is called, again, the primary somatosensory cortex. When we want to respond to something, there's another structure just in front of this primary somatosensory cortex called the primary motor cortex. And it's actually located at the very back end of the frontal lobe. A weird kind of effect if we're looking for kind of unusual things to take note of. And this particular structure, this primary motor cortex, is responsible for our ability to initiate a lot of the movement that we engage in. Now, for our motor system, it's probably important to note that we have a multitude of different areas within our brain that are critical in our motor skills. But this primary motor cortex is the place where many people think that the first inklings of movement are started. And again, just like we have to create connections for our primary somatosensory cortex, we also need to create a ton of connections as we're growing up for our primary motor cortex to be able to efficiently and effectively do the things that we want to do. How do these structures actually develop the ability to do what we want them to do? How is it that we're able to sense things and react to those things in an appropriate manner? Well, this is actually something that spurned on a philosophical debate between psychologists that actually still persists to this day. one of the early theories that was out there was one that was proposed by a theorist named Gessel. It's nowadays called the maturational development theory. It was this notion that maybe, much like structures within the brain and other structures, our motor system and our sensory system, for the most part, were really just things that were going to naturally develop regardless of what we encountered in our environment. In essence, Gessel said, you'll learn to walk at pretty much a set age, regardless of how much you're engaging in your environment, regardless of how much you want to learn to walk. You'll run at a specific age based on your genetics and your biology, and really your expectations, your desires doesn't play much of a role in this. And even though this theory seems a little kind of stunted, most people just embraced it and accepted it for a long period of time. That essentially our motor system and parts of our sensory system were just these naturally unfolding things that we didn't have much control over. Eventually, this idea was challenged by a new theory called the dynamic systems theory that suggested that actually the development of a lot of our perceptual and motor systems are a byproduct of sort of desire, the kind of recognition of what's in the environment and the motivation to then find ways to engage in those things that we want to engage with. It's essentially the byproduct of what they call perception and action. Perception being the ability to recognize what's in the environment, and action being the ability to find a way to actually engage in those things in the environment. Now, it's tough to really determine which particular theory is 100% true. It might be actually kind of a combination of the theories if we're looking for how our motor systems and our sensory systems, for the most part, develop. But nonetheless, it's probably interesting in a class like this to identify an interesting debate about how all of these systems and structures that we've talked about thus far come to do the things that they eventually come to do. It is important to note when looking at this debate that there are certain things that do seem to definitively be inherent within us. In particular, what many researchers highlight or cite when looking at some of the natural things that are a part of our nervous system are these responses that we have to stimuli, these automatic ones that we call reflexes. And we technically have a number of reflexes throughout our life, some of which we'll talk about a little bit later. But when we're born, we're actually born with a plethora of different reflexes, nerve connections that allow, when certain nerves are stimulated, for our body to create an automatic reaction to those activations of the original nerves. We sometimes call this the reflex arc, where we have specific cells in specific areas stimulated, which sends a message directly to the brain, and there's a firing back to the body without much thought involved that creates this automatic response. Some of the classic reflexes that are cited when looking at newborns, these reflexes called the rooting reflex, the sucking reflex, and the moral reflex. The rooting and sucking reflexes are really two reflexes that are very closely paired to each other. The rooting reflex is one where if you actually stimulate skin follicles on the mouth of a child, either next to it or on the cheek, somewhere in that area, the neck muscles of that child are actually activated, regardless of whether or not there's any intent behind it. And the head is immediately drawn to those things that are causing the stimulation of the cheek or the mouth or something along that lines. And what this allows the infant to do is find a way to get their mouth onto whatever it was that could have caused the stimulation of the skin in the first place. And this tends to lead to then the next reflex that's initiated called the sucking reflex, where when certain areas of the mouth are activated, typically the lips and portions of the tongue, a sucking motion is immediately initiated by the newborn infant. Again, this is not something that's done intentionally. There's no thought process, we think, going on when this happens. It's merely a byproduct of kind of pre-programmed nerve connections, nerve reflex arcs that allow newborns to do these things at the moment they're born. Another one that's often cited that I mentioned earlier is something called the Moro reflex, which we think is kind of a survival thing, where when we're startled or when something happens that kind of causes this feeling of falling, an infant will reach their arms out, arch their back, and kind of almost latch on to anything that's around. And the thought is that this motion, this kind of reaction, could potentially help a child prevent themselves from falling or maybe getting injured in ways that they could have if they weren't kind of in that rigid state. Now, what really was behind the Moro reflex is a little bit more challenging. It does have some inherent value, but why it's something that is so inherent at birth is a little bit of a mystery to researchers. The rooting reflex, though, and the sucking reflex are ones that we strongly embrace. There's also some other odd ones that are present at birth that have ones that is really endearing to many parents is something that's called the palmar grasp, where when you place something inside the hands or actually stimulate the palm of an infant, their natural reaction is to wrap their fingers around that thing that stimulated the palm and really put on quite the vice grip, a really hard grab of that. And in fact, it's really hard to get something out of the hands of a newborn infant, even though they're not necessarily consciously gripping those things. It really shows the power of how much certain nerve fibers can trigger the activation of specific muscle fibers. Many parents, of course, take the palmar grasp reaction as an indication of the child and of grabbing for a parental figure or kind of creating a bond with somebody, and probably does have that effect. But there is a belief with many of our other reflexes that there's probably some survival thing associated with it that goes beyond just enduring yourself to an adult figure. Something that's somewhat similar to this in terms of there being the stroking of some type of palm is something called the plantar grasp, or sometimes it's called the Babinski reflex. And here we're not talking about the hand, we're talking about the feet. Now, if you stroke the bottom of the feet of a child, the toes and foot actually change in their kind of motion. It's almost like a wave that happens or goes over the child. And it's a little tougher to figure out why this particular response has happened, but it's very persistent in many children. And in fact, many researchers and developmental psychologists look for the presence of that Babinski reflex to ensure that there's been healthy development inside the womb. This is something that we actually saw a video on a few modules ago, and I encourage you, if you want to get a review that video so we can go over again some of the innate things that are present in newborns. Some other ones that were mentioned in the video were the stepping reflex. Something else that was kind of just briefly touched up on was something called the swimming reflex. As I'm reflecting back on it, I think in the video that I showed you didn't actually focus on this swimming reflex, but it is one that I always like to mention because it is such an odd reflex where if you take a child and place them in water, and this has to be a newborn infant, they can eventually override this reflex, so please don't try this with any random 6-month-old. But newborn infants, when placed in water, will actually instantly, when they placed in water, hold their breath and begin stroking their legs and arms in kind of a swimming motion. And the fact that they can automatically do this is really interesting and kind of unique. I don't encourage you to do this really with any child, just in case there is something going on neurologically that prevents this swimming reflex from kicking in infants. But I can guarantee you that the vast majority of the population could swim pretty much at birth as a result of this reflex. It's just that when we start to override it, well, then we need to actually develop the skills, the motor skills, to be able to replicate something that we could do pretty much at birth. Once we focused on these reflexes, I always get a sense that people forget that these are not just things that are present in birth and that go away fairly quickly. For many of us, we have persistent reflexes that we use every single day that help us avoid some of the issues that we encounter. Some of the reflexes that are present for a couple months and then start to go away are things like the sucking reflex and some of the other startle reflexes that we looked at earlier. Most of them, though, are gone by about 6 to 8 months, the sucking reflex being the one exception to this. But there are some other reflexes that we haven't talked about that are persistent throughout life. A classic one is just coughing and sneezing, where if something activates our nose or our throat, we automatically have these coughing and sneezing reactions. I'm guessing many of you have kind of identified the power of these reflexes when you've tried to suppress a cough or a sneeze when certain areas of the nose were triggered. It's almost impossible to do this. Same thing with some other reflexes that we tend to take for granted. The lack of air will always trigger within us a yawning reflex. The processing of kind of cold or kind of the overstimulation of the skin with colder weather will automatically trigger shivers within us. And something that we tend to take for granted, but it's constantly going on, is the clearing of debris from our eyes and the assurance of extra moisture in our eyes by having blinking occur. Now, it's probably important to note that a lot of these adult reflexes can be intentionally replicated by us. We can cough on cue for the most part. We can blink on cue for the most part. But those of these things don't necessarily happen on a regular basis because of something that we're volitionally doing. They really are just byproducts of these inborn neural network patterns that persist throughout our entire life. Now, that doesn't mean that's all we have as we advance through life. We're not just born with reflexes and there's nothing else. There's lots of different systems in kind of their own way as we advance through infancy and beyond. And when we start talking about this development, one of the things that we do is break up the types of things and skills that we develop into two different categories. One particular category is called gross motor skills. Another one we'll talk about a little bit later is called fine motor skills. But gross motor skills doesn't involve things that are disgusting or icky. When we're talking about gross motor skills, we're talking about motor skills that are developed through the development of large muscles and muscular connections and systems throughout our body. And they can focus their attention on a number of different things. We're talking about early gross motor skill development for infants. Most of the focus is on postural development, the ability to hold things up or balance things. And one of the first things we dedicate a lot of our muscular focus on is just being able to do something as simple as hold our heads up and move our heads the way we want them to be moved. And it actually usually takes most newborn infants a couple weeks before this is possible. There's always some variety when we talk about development of gross motor skills. Some newborns actually have developed the muscular strength and the nerve connections to actually hold their heads up on birth. Others might take a month or so before they're able to hold their heads up successfully. This is something that's sometimes tied to birth and kind of when a child is born, where if they're born at exactly 40 weeks or 38 weeks or somewhere around there. But yeah, when we see kind of an aggregate statistic, we see on average most kids tend to be able to hold up their heads at about 2 weeks, and it's one of the first gross motor skills that are developed. As we start to advance more, the focus tends to kind of work its way down towards the body, being able to support itself. Sitting becomes something that most kids really start to focus on at about 2 months, even though it's not a guarantee that sitting is smooth. Many kids who start to develop this skill will sit for a little while and then accidentally activate, say, their legs or their back or move their head in a way that causes them to get off balance and they'll eventually topple over. But at about 2 months, the process of sitting starts to become a doable thing for many newborn infants. Eventually, they're not only able to sit well supported, but usually about 6 months, these children have kind of mastered the sitting process and can sit on their own. As very shortly after, many kids, once they get comfortable with sitting, tend to start looking toward the next step, which is typically standing. Now, there are many children that will go from sitting to crawling and then standing. There is a decent percentage of the population that will actually go from sitting to some type of a stand within about 2 to 3 months, and then transition from that stand to kind of a first couple steps. Now, most children walk for the very first time on their own, unaided, at around 1 year of age. But much like a lot of other types of motor skills that we're going to talk about later, there's a lot of variability on this particular timeline. Some children will walk at 8 months, 9 months, and they might be a little bit ahead of their time, but it's not necessarily something that's that unique or that exciting slash worrisome for developmental psychologists. If a child doesn't walk until they're 14, 15 months of age, this also isn't necessarily an indication of problems to come or cause for celebration either. It's just merely a time when a child developed the muscular strength and the nerve connections to be able to actually do this very difficult thing of walking. But it's important to note that even when a child can start to walk at about 1 year of age, there's still a lot of work to do. Most children tend to walk on carpeted or extremely flat wood floors for the very first time, and they work their way up to different types of terrain that's maybe a little bit more unsteady, maybe a little bit harder, maybe a little bit more slippery, and also terrain that tends to have different angles tied to it. So even though most kids do take their first step at around 1 year of age, even 2-year-olds are struggling sometimes to walk successfully when they have, say, a steep hill or a slippery road that they're trying to navigate on. Exposure to things does impact how well many infants develop some of their walking skills, but by the time we're 2, most of us have really mastered the walking thing and been able to kind of navigate in a multitude of terrains, and eventually then they can turn their attention to more complex gross motor skills that need. In particular, when a child gets to about 1 year to 2 years of age, in addition to kind of focusing attention on that walking process, there is focus on kind of moving in ways that's more complex. Being able to climb stairs and go downstairs is a major focus for many children in their first 1 year to 1.5 years of life. Then being able to do things like walking backwards and, say, kicking or throwing something, which can actually throw off your center of gravity, is a great focus for many kids. But all of these developments are kind of gradual processes that are constantly being fine-tuned and also individualized processes. I always like to show this chart that you see here on this slide because it highlights that even though we tend to say, at about 1, this is going to happen, when it happens at about 1 for many different tasks varies a lot. Same thing with some of the earlier things that we discussed in kind of the last slide. Being able to sit on your own without support does usually happen at around 6 months, but there are many 4.5, 5-month-olds that are sitting on their own without support already. There's also many that sit on their own without support by about 8 months. And if we're looking for what causes this change, again, we can go back to the different maturation theories that are out there. And even if we can't necessarily use the evidence that we have in front of us to definitively say which theory is correct, it's probably important to note here that the variability that we see in terms of when these things are developed doesn't usually correlate very much with physical ability later in adulthood. So I'm sure many of you know some very cocky, excited parents because their child walked at 8 or 9 months, and ones that are sheepish because it took their child until, say, 1.5 years to walk. Please understand that really does mean almost absolutely nothing in the lifespan of these children. Obviously, if there's some developmental thing or a major physical ailment that's causing a child to be stunted in the changes that they're undergoing, interventions and kind of identification of these problems is essential. But for most children, they're going to just develop these skills when they develop these skills. And once they're there, they tend to just kind of align themselves with their peers after about the age of 2 to 3. This is where individual differences do start to really emerge. Most kids are working on something like hopping or running and running and then landing in a jump around 3 years of age. But some, if they're not really pushed physically, don't develop these skills until about 4 years of age. There are, however, some exceptions to this where many kids can start hopping or running into a jump at, say, 2 years of age. So it's not a universal thing, but what we see usually is that the gross motor skills are really developed enough in most kids so that by around 3.5, 4, most kids have the ability to run, even if it's kind of an awkward type of run that we sometimes see with kids. By about 5, most of us do usually have the ability to not just walk downstairs, but walk downstairs without assistance. That means no holding on to railings, no needing somebody to kind of catch us if something does go wrong. And this also coincides with much more coordinated movements that kids start to be able to do. I know it's kind of a joke, but being able to chew gum and run at the same time is actually really challenging for many children. And sadly, many of them do tend to choke on their candy or gum if they're trying to run and do it at the same time. But as we get to around 4.5, 5, the brain does develop the ability to sort of multitask, to allocate resources to multiple areas of our primary motor cortex so we can do multiple things at the same time, physically do multiple things at the same time, and also coordinate them together so we can do more elaborate things. And this allows children for the very first time to do things smoothly, like shoot a basketball or swing a baseball bat or kick a soccer ball in a fashion that's more elegant, we might say. And after about 5, what we tend to see is that experience and training really dictates how much more advanced we get with that coordination. It's not that at 5, then kids start to differentiate. You can see very easy differences from kid to kid at around 2 to 3 years of age. But those differences become even more pronounced as sports and other types of events that really push specific types of gross motor skills start to kind of emerge. And in fact, many kids start to pursue specific sports based on some of the gross motor skills that they themselves identify as kind of developing better within them. And this is something that tends to be persistent throughout life at this point. Usually, if you start to really focus on specific movements, you start to really develop better gross motor skills in those areas that relate to those movements. If you don't do something, you don't engage in specific acts, well, those gross motor skills might be underdeveloped or just as not as developed as other individuals. And this really highlights a need to start pushing kids to not necessarily get themselves in danger, but to work on their coordination and work on their movement. Not because we're aiming to have all of our children be professional athletes, but because that coordination and that ability to move can be helpful in engaging in the environment and possibly avoiding certain random disasters that befall us on a day-to-day basis. When we get past childhood and we've started to develop specific skills, it's really important to note here that for around 20 to 30 years, most of the changes that we see in our motor system are really linked to refinement and activity-specific growth and decline. Essentially, the more we do something, the better we get at it and the faster we are at it, all the way up until our mid-30s. Usually at around 35, 30-ish, maybe, depending upon the activity that we're talking about, we finally start to see kind of a leveling off and a slow, gradual decline in some of our gross motor skills. And usually the first thing that we see is a slight decrease in the speed, the twitch speed of some of these gross motor skills. That's also paired with some of the coordination challenges that we kind of took for granted once we got into our adolescence, but they kind of come back to get us, where maybe we're not in our 50s incapable of walking and chewing gum again, but honestly, walking and chewing gum, if you're not doing it on a regular basis, can start to become a little more challenging for 50-year-olds. But like many of the things that we've talked about, what we tend to see is that this decline, this gradual loss of these gross motor skills, tends to be very activity specific. If you're playing soccer every single day or basketball every single day, those skills will persist with you long into your 40s, 50s, and beyond. You might not be quite as strong. You might not be quite as fast as you were when you were, say, 25, 30, but some of those kind of coordinated movements that you've developed tend to persist unless you really stop doing those activities for an extended period of time. And this brings us to another closely related type of motor development, the motor development of something that we call our fine motor skills. Think of gross motor skills as kind of the big, robust movements that we do, and fine motor skills being all about the tiny, twitchy, small movements that we do. This can be something as simple as moving our fingers in a way that allows us to knit or play piano or do something on our phone. And it can kind of evolve into other things, like our ability to quickly move our mouth or quickly react to things in the environment. And what we see with these fine motor skills that are very kind of instantaneous reactions to things is much like with our gross motor skills, we tend to see an ascent, a growth in the development of these fine motor skills all the way until mid-adulthood. That means usually from the moment we're born, we tend to have really crummy fine motor skills, the inability to really control everything. But as we work on things into our mid-30s, the specific things that we're focusing on tend to result in greater ability to do those fine tasks that we're aiming to do. And if we're looking for why this is the case, some of our friends that we talked about in the last lecture really are the major players in the ascent of these fine motor skills. What we see is neuronal migration can actually cause specific neuron clusters to travel to areas of, say, the fingers or the hands or the feet if we're using those areas of our body in abundance. And not only do we see new cells migrating to those areas, but synaptogenesis happens a lot in those areas, and the myelination process actually happens more abundantly and persists longer in the areas where we're doing those tasks on a repetitive basis. And this experience can allow a lot of these fine motor skills to persist within us, not just until our 30s or 40s, but sometimes even our 50s and 60s. In fact, the only thing that we see really declining with our fine motor skills if we're persistently doing something is how quickly we can do some of these fine motor tasks. And a lot of this kind of descent doesn't relate to the death of a bunch of cells or the loss of myelination when we're talking about fine motor skills. And again, this can happen if we're not active, but if we are active and doing something, we still tend to slow down on these things a little bit because of something that we link to what's called neural noise, where neurons eventually, even though they're communicating effectively for the most part, start sometimes misfiring and recognizing things that aren't there, or maybe just sending random messages to other cells. And this kind of noise in the data, this kind of disruption, causes us to kind of be a little bit more hesitant in our motor system and our sensory system. And it slows down some of those fine twitch movements that we aim to do in a lot of the different activities that are out there. This decline, again, can be very gradual if we're extremely active in something. But if we're not doing something on a regular basis, this descent into our late 30s and 40s and beyond can be very noticeable. And this really, again, highlights that need for that use it or lose it principle that we've been referencing a number of times throughout these last few lectures. And this end of the kind of fine motor topic is where we're going to end this particular discussion. We've covered, though, how we're able to sort of take in information through our sense of touch. We sort of just danced on it, and definitely how we're able to react to that information when talking about our motor system. We're going to transition our attention to some other sensory systems that we've overlooked so far. In particular, we're going to focus our attention on both vision and hearing. We'll allude a little bit to the other two ones of taste and smell, but we're going to try to dedicate enough time and energy into this hearing and vision processes to understand how many of our other sensory systems are undergoing change as we develop from infancy to adulthood. But for today, we're going to close up here. I hope you got a lot out of this, and I hopefully will see you all very soon. Take care.